In today's video, you're going to see 5 rocks that you can break to find diamonds and other precious stones like rubies and emeralds inside them. These rocks are known as host rocks, and if you know how to identify them, it might be that when you open them, you'll find some of these treasures that can be worth anywhere from hundreds to thousands of dollars, depending on the stone you find. For example, what you're seeing right now on your screen is a piece of kimberlite with a diamond stuck in it. Of course, most people would never imagine that this rock had a diamond like this inside it. But when you break this rock the right way, in the right place, what's inside it can change your life. And the most impressive part is that if you know how to identify these rocks, you'll see that many of them are within reach of anyone who knows what to look for.
Oh my God, oh my God.
And that often they don't even need to be broken to access what's inside, because erosion has already done that. There are 5 specific types of rock that, when found in the correct geological environments, can hide diamonds, sapphires, garnets, tourmalines, and other gems of high commercial value. The problem is that most people don't know how to recognize these rocks. They walk right past them, think it's just old rock, and miss the chance to find something valuable that was literally under their feet. That's why, in today's video, you're going to learn exactly what these 5 rocks are, how to identify them in the field, what type of gem each one can hide, and most importantly, how to break them safely and efficiently to expose what's inside. Because there's no point knowing that the rock has potential if you don't know how to access the material without destroying it or hurting yourself in the process. Of course, not every rock is going to have a gem inside. In fact, most of them won't have anything. And that's why you need to read the right signs, recognize textures, colors, mineral associations, and geological context, so you don't waste time after all. Even if you break 5, 10 rocks without finding anything, just one quality gem is enough to make up for all the effort. So stick with me until the end, because you're going to leave here knowing exactly what to look for, where to look for it, and how to turn an ordinary rock into a discovery that can completely change the way you see the ground you walk on. The first rock you need to know is kimberlite, and if there's one stone on this entire list that deserves your full attention, it's this one. Kimberlite is a rare type of volcanic rock that originates more than 90 miles deep inside the earth, in the upper mantle, where temperatures and pressures are so extreme that carbon crystallizes into diamond. When a kimberlite eruption occurs, which is an exceptionally rare event, it violently shoots upward through the crust, carrying with it fragments of mantle rock and any diamonds that form there. That means kimberlite doesn't create diamonds, it transports them. And that's exactly why finding kimberlite in the field can be a strong indicator that diamonds might be present. In its fresh form, kimberlite is a dark greenish-gray rock with a fine-grained matrix, often containing visible crystals of olivine, pyrope garnet, and other mantle minerals. Over time, exposure to weathering turns it into a softer, yellowish or reddish material that's easier to break apart. In some cases, kimberlite bodies are so weathered that they look like clay or compacted dirt, which is why many prospectors walk right past them without realizing what they're looking at. But if you know the signs, you can spot kimberlite even in its altered state. One of the most reliable field indicators is the presence of pyrope garnet, a deep red to purplish red mineral that forms under the same high-pressure conditions as diamond. If you find small, rounded garnet grains scattered on the surface or mixed into the soil, especially in areas with a history of volcanic activity, that's a strong signal that kimberlite might be nearby. Other indicator minerals include chrome diopside, which is a bright green pyroxene, and ilmenite, a black metallic oxide that often appears as small, shiny grains in heavy mineral concentrates. When you start seeing these minerals together, you're likely dealing with material that came from deep in the mantle. Breaking kimberlite requires a different approach than breaking most other rocks. Because it's often soft and crumbly, especially in weathered zones, you don't need heavy hammers or chisels. A small rock pick and a sturdy bucket are usually enough. The goal is to break the rock into manageable chunks and carefully inspect each piece for indicator minerals, or, in rare cases, small diamond crystals. Diamonds in kimberlite are usually octahedral in shape, with a greasy or resinous luster that stands out from the duller matrix. They're also much harder than any other mineral in the rock, so if you find a clear or slightly yellowish crystal that scratches glass with ease, you might be holding something extremely valuable. In the United States, kimberlite occurrences are known in states like Colorado, Wyoming, and Montana, though most of these deposits don't contain gem-quality diamonds in commercial quantities. Still, even finding indicator minerals in these areas is significant because it confirms the presence of deep mantle material and opens the door to further exploration. In other parts of the world like South Africa, Russia, and Canada, kimberlite pipes have produced some of the largest and most valuable diamond deposits ever discovered. And the process of finding them always starts the same way, by recognizing the rock, understanding its context, and knowing what to look for inside. Now, pegmatite is probably the easiest to recognize in the field. Pegmatite is an igneous rock that forms during the final stages of granite crystallization when the remaining magma is extremely rich in water and dissolved elements like lithium, boron, and fluorine. Because of this high water content, crystals have more time and space to grow, which is why pegmatites are famous for their unusually large mineral grains. In a typical pegmatite, you can see quartz crystals the size of your fist, feldspar blocks as big as bricks, and sheets of mica that peel off in layers several inches wide. But what makes pegmatite truly valuable is that it's also the primary host rock for gemstones like tourmaline, beryl, and topaz. Tourmaline appears in pegmatites as long, striated columns that range in color from jet black to deep green, pink, blue, and even multicolor combinations known as watermelon tourmaline. The crystals grow perpendicular to the host rock and often stand out visually because of their darker color and strong linear striations running along the length of the prism. In some pegmatites, especially those with pockets or vugs, you can find well-formed tourmaline crystals that are completely free of matrix, making them ideal for cutting or polishing. And even if the crystal is still embedded in the rock, a careful break along the natural fracture lines can free it without causing damage. Beryl is another major gemstone found in pegmatites, and it includes several well-known varieties like aquamarine, emerald, morganite, and golden beryl. In pegmatite, beryl typically forms as hexagonal columns with smooth faces and a glassy luster. Aquamarine, which is pale blue to blue-green, is the most common variety found in pegmatites across the United States, especially in regions like Colorado, California, and New Hampshire. The crystals can range from tiny fragments to massive columns weighing several pounds, and even lower-grade material has value in the collector market. Emerald, which is the green variety of beryl colored by chromium or vanadium, is much rarer and usually forms in specialized pegmatites associated with metamorphic rocks. Topaz is the third major gemstone associated with pegmatites, and it's one of the hardest minerals you'll encounter in the field, with a Mohs hardness of 8. Topaz crystals are typically colorless, pale yellow, or light blue, with sharp, well-defined faces and a strong vitreous luster. They form in the late stages of pegmatite crystallization and are often found in cavities lined with quartz and muscovite mica. Because topaz is so hard and brittle, breaking it out of the host rock requires precision. The best approach is to use a small chisel and carefully work around the crystal, following the natural cleavage planes of the surrounding minerals. If you try to force it, the crystal can shatter along its perfect basal cleavage, leaving you with worthless fragments instead of a cuttable gem. In the field, recognizing pegmatite is straightforward. Look for light-colored rock outcrops with very coarse texture, often appearing as veins or dikes cutting through darker metamorphic or igneous rocks. In road cuts, pegmatites stand out because of their large, blocky crystals and pale color, which contrast sharply with the surrounding material. Once you've identified a pegmatite body, the next step is to examine the weathered surface and the loose material at the base of the outcrop. Many gemstone crystals are already partially freed by natural erosion, and with minimal effort, you can extract them from the soft, decomposed matrix. And if you find one tourmaline or beryl crystal, there's a good chance that more are nearby, because pegmatites tend to form gem-rich zones rather than isolated occurrences. The third rock on the list is marble, a metamorphic rock formed when limestone is subjected to high heat and pressure. Pure marble is white and composed almost entirely of calcite, but most natural marbles contain impurities that give them color and, more importantly, create the conditions for gemstone formation. When marble comes into contact with igneous intrusions or hydrothermal fluids, a process called metasomatism occurs, where new minerals crystallize in response to chemical changes in the rock. This is how corundum, which includes ruby and sapphire, forms in marble. In aluminum-rich marbles, especially those exposed to high temperatures, corundum crystals grow as hexagonal prisms or barrel-shaped grains. Ruby, which is red corundum colored by chromium, is the most valuable variety, but blue, pink, and even black sapphires can also form in the same environments. Breaking marble to find corundum requires patience and a good understanding of the rock structure. Marble is moderately soft, with a hardness of 3 on the Mohs scale, so it breaks easily with a hammer. The challenge is identifying which layers or zones are most likely to contain gemstones. Look for sections of the marble that show color banding, especially zones with a pinkish, grayish, or bluish tint, as these often indicate the presence of corundum or spinel. Once you've located a promising zone, use a chisel to carefully break the rock along its natural bedding planes. Corundum crystals are much harder than the surrounding marble, so they'll resist scratching and stand out visually as solid, well-formed grains. Even if the crystals are small or heavily included, they're still valuable as mineral specimens or as raw material for lapidary work. Schist is a medium to high-grade metamorphic rock characterized by its foliated structure and high mica content. Schist forms when shale or mudstone is subjected to intense heat and pressure, causing the minerals to recrystallize into aligned sheets. This alignment gives schist its characteristic sparkle, which comes from countless tiny mica flakes reflecting light. But beyond mica, schist often contains valuable accessory minerals like garnet, kyanite, and staurolite. Garnet is by far the most common gemstone found in schist, appearing as dark red, wine-colored, or brown crystals that range from pea-sized grains to fist-sized specimens. In some schists, especially those derived from aluminum-rich protoliths, kyanite forms as blue and bladed crystals with a vitreous luster and perfect cleavage. Breaking schist to extract garnets is relatively simple because the rock splits easily along its foliation planes. Use a flat chisel and a light hammer to pry apart the layers, exposing the internal structure. Garnets often weather out naturally and can be found loose in the soil at the base of schist outcrops, but the best quality crystals are usually still embedded in the host rock. Once you've exposed a garnet-bearing layer, carefully work around the crystal using the tip of the chisel, taking advantage of the schist's natural weakness. With minimal effort, you can pop the garnet free without damaging it. And if you find one garnet, keep breaking more layers, because garnets and schist tend to occur in clusters rather than as isolated grains. Now we get to basalt, a dark, fine-grained volcanic rock that forms from rapidly cooled lava. Basalt itself isn't particularly valuable, but it's the host rock for some of the most beautiful and sought-after gemstones in the world, including amethyst, agate, and peridot. These gemstones form in gas cavities, also called vesicles, that were trapped in the lava as it cooled. Over time, mineral-rich groundwater seeps into these cavities and deposits layers of silica, forming agate and chalcedony. In some cases, the silica crystallizes into quartz, which can be colorless, smoky, or, in the presence of iron impurities, deep purple amethyst. Peridot, which is a gem-quality variety of olivine, forms directly in the basalt matrix and appears as small, olive-green crystals with a glassy luster. Breaking basalt to find geodes and gemstones requires a different technique than the other rocks on this list. Basalt is hard and dense, so you'll need a heavy hammer and safety glasses. The goal is to look for rounded, hollow-sounding nodules or sections of the rock with visible cavities. When you tap on a basalt geode with a hammer, it often sounds different from solid rock, producing a slightly hollow or ringing tone. Once you've identified a promising nodule, place it on a stable surface and strike it firmly along its equator, not directly on top. This helps split the geode cleanly in half, exposing the internal crystals without shattering them. And even if you don't find a perfect amethyst geode, smaller agate nodules and chalcedony-filled cavities are still valuable and widely collected. In other words, finding gems in nature is not a matter of luck, but of applied knowledge. Each of these rocks has a different geological formation, and each of them hides specific crystals. The difference between walking right past and making a valuable discovery lies in knowing how to read the signs, recognize textures, understand geological context, And, most importantly, having the courage to break the right rock at the right time. Now let's suppose that during a trail hike, you pass by a road cut or explore a gravel area near a river. You see a rock with coarse texture, opaque. It looks like a crystalline fragment. Would this be a quartz, topaz, or something more special like a ruby or diamond? Well, to know that you can perform hardness, density, and refraction tests to be sure of what you found. And that's exactly why we created the book Gemology Journey for Beginners, available now on Amazon. It was written specifically for people who want to learn how to identify precious stones with simple, practical, and accessible tests that can be done at home without professional equipment. Inside the book, you'll find detailed explanations about hardness, density, luster, cleavage, and all the physical characteristics that differentiate a valuable gem from a common stone. It's like having a complete field guide always at hand, ready to be consulted every time you find something that seems special. But if now is not the right time for you to get the book, no problem. You can still keep learning all of this for free here on the channel by subscribing and watching the next video that's appearing on your screen right now. Each episode was created to help you see what others ignore, and who knows, make your own discovery someday. Thanks for liking and subscribing. Good luck, Gem Hunter.
There is a state park in the United States where anyone can walk in, dig the ground with their bare hands, and legally leave with a diamond in their pocket. This is not a legend. This is not clickbait. More than 35,000 diamonds have already been found there by ordinary visitors, without specialized equipment, without a mining license, without any advanced technical knowledge. And that is just one of the 5 places you are going to learn about in this video. Because the vast majority of people have no idea that diamonds can be found legally, and that the signs pointing to where they are sitting right there in plain sight for anyone who knows what to look for. They drive past these places, hike through them, camp near them, and never stop to look down. And the ground is full of information. In this video, you are going to see exactly that. 5 real locations with public access or accessible permits where diamonds have been found and continue to be found to this day. Beyond the locations, you are going to understand the geology that makes each one of them work, the minerals that tell you when you are standing on the right kind of ground, and what to do when you find a stone you cannot identify on the spot. Stay until the end, because each of the 5 locations has a very different geological character, and understanding that difference is what will change the way you read the terrain when you are actually there. Before we talk about specific locations, there's one thing you need to wrap your head around first, because without it, none of the rest will make sense. Diamonds don't form anywhere near the surface. They form incredibly deep underground, more than 90 miles below your feet, under so much pressure and heat that it's almost impossible to picture. And the only reason they ever reach the surface is because of a very specific and rare kind of volcanic event. One that shoots a column of rock upward from deep inside the earth all the way to the top. That column of rock has a name, kimberlite. And wherever kimberlite exists, diamonds can exist too. Think of it like a pipe drilled through the earth from the inside out. The eruption forces that pipe upward, cutting through every rock layer in its way. And as it moves, it carries diamonds along for the ride. When it finally cools and hardens at the surface, it leaves behind what geologists call a kimberlite pipe. And these pipes are essentially natural diamond delivery systems from the deep earth to the surface. They don't look dramatic from the outside. No glowing crater, no obvious sign, just a particular type of dark, heavy rock sitting in the ground, waiting to be recognized. Now, over millions of years, rain, wind, and rivers slowly break those pipes apart and wear them down. As they erode, the diamonds locked inside get released into the surrounding landscape. Water picks them up and carries them downstream. They settle into riverbeds, collect in the curves of rivers where the current slows down, and accumulate in old gravel deposits that may have been active waterways thousands of years ago. This is why so many diamond discoveries happen in and around rivers and creek gravels, sometimes a long way from where the original pipe was located. And here's something that really helps when you're out searching. Diamonds don't travel alone. They always bring company. There's a group of specific minerals that form under the same deep earth conditions as diamonds, and they consistently show up in the same places. The most useful one to know is Pegmatite garnet, which appears as a deep red to purplish rounded grain, noticeably denser than the common rocks around it. Then there's ilmenite, which is dark and heavy with a slightly metallic surface, and chrome diopside, which is a bright, vivid green. When you find these minerals concentrated in a gravel bed or a stream deposit, that's the ground talking to you. It's telling you the geology of that area is consistent with diamond-bearing formations. You're not guessing anymore, you're following a trail. There's also a close cousin of kimberlite called lamproite, and it works in essentially the same way. It's another type of deep volcanic rock that can carry diamonds to the surface, and it forms the same kind of pipe structure. The most famous publicly accessible diamond hunting location in the United States sits directly on a lamproite pipe, which we'll get to in the next part. The Australian Argyle mine, which for decades was one of the biggest diamond producers in the world, was also a lamproite deposit, so this rock type is far from minor. It's also worth knowing what kimberlite actually looks like when you come across it in the field, because recognizing it completely changes how you evaluate a location. When it's fresh and unweathered, kimberlite is a dark greenish gray to bluish rock, fairly compact, and you can often see individual mineral grains in it if you look closely. When it's been sitting at the surface for a while and weathering has set in, the color shifts toward yellow-brown as some of the less stable minerals break down. One interesting side effect of kimberlite weathering is that it changes the chemistry of the surrounding soil, and that chemical change sometimes affects the plants growing nearby. You might notice patches of slightly different vegetation in an area dominated by kimberlite-derived soil, a subtler and different mix of plants compared to everything around it. Experienced prospectors learn to notice these environmental hints as indirect signs that they're in the right kind of ground. The geometry of these pipes also matters and helps you understand what you're dealing with at the surface. The very top of a kimberlite pipe, the part closest to where the volcanic eruption broke through, is called the crater faces. It's a zone of fragmented, broken-up rock, essentially a mix of kimberlite and everything the eruption chewed through on its way up. Below that is the diatreme zone, which is the main body of the pipe extending deep into the crust. Diamonds can be found throughout all of these zones, but when you're searching at the surface in an area where erosion has done its work over millions of years, you're almost always dealing with material that was once part of that upper crater zone, broken down over time and scattered across the landscape by water. Which brings us to the last concept you need before we get into the actual locations: placer deposits. When a kimberlite pipe erodes, the diamonds it releases don't just disappear. They're incredibly hard and chemically stable, so they survive the journey downstream intact. They eventually settle in specific spots along river systems, particularly on the inside curves of bends behind natural obstacles like large boulders, in pools where the current loses energy, and in old terraces that were once active riverbeds but are now dry ground above the modern waterline. These concentrated zones of heavy minerals are called placer deposits, and working them is one of the most productive strategies available to any prospector who doesn't have access to heavy excavation equipment. Understanding this concept is what makes the difference between searching randomly and searching intelligently. The first location is Crater of Diamonds State Park in Murfreesboro, Arkansas, and this one is truly in a category of its own. It's the only diamond-bearing site open to the general public in the entire United States where you're legally allowed to keep whatever you find. The park sits directly on top of the Prairie Creek lamproite pipe, one of the largest exposed diamond-bearing volcanic structures in North America. And the search area is a large open field of about 37 acres that gets plowed on a regular basis so that fresh material is always being brought up to the surface for visitors to search through. The soil across that field has a very particular look once you know what you're seeing. It's clay-heavy, and the color ranges from a warm yellow-orange to a pale greenish-gray depending on where you're standing, reflecting the different stages of weathering of the lamproite underneath. When you're walking that field, you're literally walking on the eroded surface of an ancient volcanic pipe. Diamonds found here come in several colors, white and yellow being the most common, but brown occurring as well. And the park keeps detailed records of every significant find made by visitors over the years. Stones of a carat or more turn up regularly, and the total count of diamonds found by the public since the park opened has passed 35,000. The most effective approach at this location, and the one the park staff consistently recommends, is to search after a heavy rainfall rather than digging deep into the soil. Rain does a natural sorting job. It washes the lighter clay particles away and leaves the heavier minerals sitting in small low spots, channels, and depressions across the surface of the field. Those low areas after rain are exactly where you want to focus your attention. The diamond itself behaves differently from the surrounding rocks when it's wet. It has what's described as a greasy or oily luster, a surface reflection that doesn't look quite like glass and doesn't look quite like rock either. It's subtle, but once you've seen it, it becomes recognizable. Density is your other constant guide. Diamonds are noticeably heavier than you'd expect for their size, and picking them up feels different from picking up a similarly sized piece of quartz or limestone. Many of the most significant finds at Crater of Diamonds have come from visitors who noticed that something simply looked out of place, a slightly wrong shape, a luster that didn't fit, a weight that didn't match expectations. That combination of patience and basic geological awareness is what separates people who leave with something from people who leave with nothing. The second location takes us to the Colorado-Wyoming state line region, specifically to what geologists call the State Line Kimberlite District. This district straddles the border between the two states in the area around Fort Collins to the south and Laramie to the north, and it contains more than 40 individual kimberlite pipes, making it one of the most geologically significant kimberlite fields anywhere in North America. Most people traveling through that corridor have absolutely no idea what's sitting beneath the landscape around them. The pipes are embedded in rolling, high-altitude terrain, and decades of natural erosion have scattered indicator minerals across a wide area of creek gravels and hillside debris. Doing this location right takes a little preparation because land access varies quite a bit depending on exactly where you are. Some portions of the district fall within public land administered by the Bureau of Land Management, where recreational prospecting for personal use is generally allowed under federal guidelines, though you should always confirm the current rules before going out. The star indicator mineral in this district is pyrope garnet, and it's been documented in creek gravels throughout the region by both amateur prospectors and professional geologists. When you find a gravel bar or stream bed concentrate loaded with dense, rounded, reddish-purple grains, you're in exactly the kind of ground you're looking for. The garnets from this particular field tend to have a distinctive purple-red tone that's different from the more common almandine garnets that show up in the metamorphic rocks all through the Rocky Mountain region. And learning to tell those two apart, mostly through density and that specific color quality, is a skill that pays off significantly once you're working this terrain. The kimberlite pipes in this district also tend to leave a subtle physical mark on the landscape. A gentle circular or elliptical depression where the softer volcanic rock has eroded slightly faster than the harder surrounding country rock. When you start noticing these depressions and orienting your search around them, you're prospecting with geological intelligence rather than just hoping for luck. The third location stays in Arkansas, but moves beyond the boundaries of the state park, out into the broader river system that drains the Prairie Creek area. This is the alluvial extension of the same deposit. The diamonds that eroded from the Prairie Creek pipe over thousands of years didn't all stay within the park boundaries. Water carried them downstream into the tributaries of the Arkansas River and beyond. And historical accounts from early settlers and prospectors in the region document diamond finds in streams well outside what is now the park. That dispersal pattern is geologically expected and well supported by the evidence. Secondary placer deposits, concentrations of heavy minerals in old gravel terraces and active stream gravels can exist throughout the drainage area of any river system connected to a diamond-bearing source. Searching these secondary deposits is a different kind of challenge from working the park. There's no plowed field waiting for you, no staff to orient you, no map marking the productive zones. You're reading the river system directly, looking for the kinds of places where heavy minerals would naturally concentrate. The inside bends, the pools behind large obstacles, the elevated terraces that were once active riverbeds. It takes more skill and more patience, but the geological logic is sound, the history supports it, and the absence of crowds makes it genuinely appealing for anyone willing to put in the work. The fourth location brings us to the Lucite Hills Volcanic Field in Wyoming, in the Green Mountains area east of Rock Springs. This is a lamproite field, geologically comparable to Crater of Diamonds in terms of the type of rock involved, but dramatically different in terms of how much attention it has received from the public. The Lucite Hills contain some of the best preserved lamproite outcrops found anywhere in North America, sitting in a wide-open high desert landscape where much of the surrounding land is publicly accessible. Indicator minerals including chrome diopside and pyrope garnet have been documented in the gravels of this area, and because so few people have explored it systematically compared to sites in Arkansas, it remains genuinely open territory. One detail about this field worth paying attention to is the effect that lamproite-derived soils have on the vegetation around them. The unusual chemical makeup of these soils, elevated in potassium and magnesium relative to surrounding terrain, sometimes creates visible transitions in plant communities, patches where different species grow or where familiar species grow in unusual densities. These vegetation changes are subtle, but in an otherwise uniform desert landscape, they stand out to anyone who's learned to look for them, and experienced prospectors use them as a natural overlay map pointing toward the volcanic material underneath. The fifth and final location takes us across the border into Canada, to the kimberlite-rich terrain associated with the Northwest Territories and the surrounding regions of northern Ontario and Quebec. The Lac de Gras kimberlite field in the Northwest Territories is one of the most prolific diamond-bearing geological zones ever discovered, and it underpins major commercial operations that have been running for decades. But beyond the active mining areas, the surrounding territory contains additional kimberlite pipes that have been identified but never fully developed, and access to some of this terrain is possible through guided rockhounding tours that operate legally with the appropriate permits. What makes the broader region especially interesting from a prospecting standpoint is the role that glaciation played in the landscape. The massive ice sheets that once covered this entire region were enormously effective at scraping material off kimberlite pipes and redistributing it across vast distances. The result is that indicator minerals, pyrope garnet, chromite, and ilmenite in particular, show up in glacially transported gravels over an enormous area, making it possible to detect the signature of diamond-bearing rock even when the original pipe is deeply buried or far away. That glacial dispersal acts like a wide-angle lens, spreading the clues across a much larger search area than you'd have in a non-glaciated region. What ties all five of these locations together is the same underlying story. Ancient volcanic activity deep in the earth brought diamond-bearing rock to the surface, and then water, time, and in some cases glaciers did the work of concentrating those minerals into places where a person with the right knowledge can actually find them. The geology does the heavy lifting. Your job is to learn to read it and put yourself in the right place at the right time. Knowing where to go is one thing. Knowing what to actually do when you get there is something else entirely. And this is where a lot of people fall short. A raw diamond in the field looks nothing like what you'd see in a jewelry store. There's no sparkle, no facets, no obvious glitter sitting on top of the gravel screaming at you to pick it up. It's a rough stone, often covered in clay or iron staining, sitting among hundreds of other rough stones that all look roughly similar at a glance. The difference between finding one and walking past it comes down entirely to technique and knowing what specific properties to look for. The most reliable and practical technique for working alluvial deposits, whether that's an active stream, a gravel bar, or an old dried-out terrace, is wet screening. The process is simple. You fill a wire mesh screen or a classifier, which is just a bucket with a mesh bottom, with material scooped from the gravel bed. You submerge that screen in water and shake it back and forth until all the fine silt, sand, and clay have washed through the mesh and drained away. What stays behind in the screen is the coarse, heavy fraction of the material, the stuff that's too dense and too large to wash through. You dump that concentrate onto a flat surface, spread it out, and go through it carefully piece by piece. In that concentrate, you're looking for density that feels wrong for the size of the stone. A surface luster that's different from quartz and feldspar, and the blocky or slightly rounded octahedral crystal shape that raw diamonds often display. Some diamonds are perfect crystals. Others are fragments or irregular shapes from having been broken during transport. Both are worth catching. At Crater of Diamonds, the approach is a bit different because you're working a plowed clay field rather than a stream bed, and digging deep isn't the strategy that works there. What works is systematic surface scanning, walking slowly across the field in straight parallel lines and examining the ground at close range as you move. The single most important tool you can bring to that field is a small spray bottle filled with water. Any stone that catches your eye for any reason gets a rinse. When the surface is wet, the true character of the stone becomes visible. A raw diamond when wet shows what gemologists describe as an adamantine to greasy luster, a surface reflection that has a slightly oily quality to it, different from the sharp, glassy shine of wet quartz or the flat, dull surface of most common rocks. It's not always dramatic, but it's consistent. And once you've held a raw diamond and looked at it wet, the comparison becomes clear. In terms of equipment, there's genuinely no need to invest in anything complicated or expensive. A small hand trowel for scraping and moving material, a wire mesh classifier, which costs almost nothing at any garden or prospecting supply store, a spray bottle, and a loupe with at least 10 times magnification are the essentials. The loupe is particularly important because it lets you do one of the most reliable field checks available, looking for trigons. Trigons are tiny, triangular etch marks that appear naturally on the flat faces of diamond crystals during their formation deep in the earth. They're not carved or polished. They're a natural growth feature, and they don't appear on any other mineral. When you put a stone under 10 times magnification, and you can see those small triangular patterns on a flat crystal face, that's very strong evidence that you're holding a real diamond. You still want a professional to confirm it, but trigons under a loupe are one of the clearest signals you can get in the field without laboratory equipment. The mineral that fools beginners more than any other is quartz, and it's worth spending a moment on why. Clear or milky quartz crystals can be transparent. They catch light well. And when you're excited and searching hard, your brain wants them to be something special. The most reliable way to tell quartz from diamond in the field is weight. Pick up 2 stones of similar size, 1 quartz and 1 suspect, and diamond will feel noticeably heavier in your hand. Diamond is one of the densest minerals you'll encounter in these environments, and that density difference is something you can actually feel once you know what to expect. Zircon is another common source of confusion, particularly in gravel concentrates, because it can be very lustrous and has a higher density than most minerals. The distinction there is in crystal shape. Zircon typically forms elongated 4-sided crystals, while diamond almost always shows that blocky octahedral form, like 2 pyramids glued together at the base. When you find a stone that you genuinely can't rule out in the field, the right move is to stop trying to force a conclusion on the spot. Wrap the stone carefully, ideally in a soft cloth or tissue, write down exactly where you found it and what the surrounding material looked like, and take it home. A gemological tester available online for a modest price can check thermal conductivity and give you a strong preliminary answer. For a definitive result, a gemologist or a university geology department can do it conclusively. The mistake people make is dismissing a stone they can't immediately identify and throwing it back into the gravel. That's how you lose something real. The underlying discipline that holds all of this together is systematic thinking. The prospectors who find things consistently are not the ones rushing through an area grabbing at every shiny stone. They're the ones who choose a productive zone based on geological logic, work it methodically from one end to the other, and document what they find, even when what they find isn't a diamond. Every pyrope garnet recovered from a gravel bar. Every ilmenite grain pulled from a concentrate. Every piece of chrome diopside spotted in a stream bed is a data point. It's the ground confirming that the source material is present in that area. A deposit rich in indicator minerals is a deposit worth returning to, worth mapping, worth working more thoroughly on the next visit. That's not just patience. That's how real prospecting works. If you made it this far, you already have knowledge that the vast majority of people who visit these places never had. You understand why kimberlite matters, what indicator minerals reveal about the ground beneath you, how to work an alluvial deposit with technique instead of luck, and what to expect when you are holding a stone that might be a raw diamond. But the next step, knowing how to confidently identify what you found before showing it to any buyer, is where most people make the most costly mistakes. People all over the world sell for a few dollars what could be worth hundreds or thousands, simply because they don't know what they are holding. And there are buyers out there who count exactly on that. That is why the book Gemology Journey for Beginners, available on Amazon, was created. It brings together in a clear and accessible way everything you need to know to identify precious stones using practical tests you can do at home without professional equipment. Hardness, density, luster, crystal form, behavior under light. Each of these criteria is explained in a way any beginner can apply. If you found something of value, this book is what will make sure you know exactly what to do with it. And if now isn't the right moment for the book, that's perfectly fine. You can subscribe to the channel for free and watch the next video that's appearing on your screen right now, where you'll keep building this knowledge one step at a time. Thanks for liking and subscribing. Good luck, Gem Hunter.
Diamonds are, without a doubt, the most coveted gemstone in the world. And as rare as it is, it can be found in several regions of the planet. But would you like to know if your area is one of them? To keep it simple, there's a very good chance you live relatively close to one of these regions. And as generic as that may sound, it's important to understand that within these areas, there are specific spots where your chances of finding diamonds are much higher. That's exactly why, in this video, you're going to learn how to find diamonds in creeks, and you'll quickly understand why we chose creeks. They're one of the best places to find gemstones like rubies, sapphires, and diamonds without needing expensive gear, heavy machinery, or advanced mining techniques. In other words, these are accessible places where you can search for gemstones hidden in the gravel that has already been sorted over thousands of years by the force of running water. These streams that cut through forests, farms, trails, and sometimes even suburban areas can quietly move and concentrate heavy minerals right in front of everyone without anybody noticing. In many locations, the best clues for diamonds are literally sitting under just a few inches of water. To give you a clear idea, the stone on your screen right now is a rough diamond. Notice how different it looks compared to the cut gems you see in jewelry stores. That's exactly why so many people end up ignoring diamonds in nature. For most beginners, these darker little stones look like nothing more than shiny gravel. And this is where things really change. Once you understand what you're actually looking at, your whole perspective shifts. Your life can change, not because you're guaranteed to find something valuable, but because every creek becomes a new opportunity to get outside and hunt for gemstones with a trained eye. But the truth is, even with all of this, a lot of people still aren't sure how to actually find and recognize a rough diamond in the wild. So in this video, we're going to break it down step by step. Which regions are most likely to host diamonds? What the main diamond indicators are in a given area? How to identify a rough stone in your hand? And how much a diamond found in a creek can realistically be worth, so you don't end up throwing away a valuable stone, thinking it was just another common rock. So the first thing you need to understand is that before you start scooping up gravel from a creek, you should follow two key steps. First, learn how a creek concentrates heavy material, and second, learn which minerals tell you that you're in a place with real diamond potential. Without that, you can spend the whole day working hard in the wrong spot and go home with nothing more than a few pretty but common stones. Let's start with the behavior of the water. In a straight section of a creek, the current is stronger in the middle and weaker near the banks. When the creek curves, the water speeds up along the outside of the bend and slows down along the inside. Lighter materials like fine sand and silt tend to stay in the faster part of the flow and keep traveling downstream. Heavier grains and pebbles start to drop out of the current where the water loses energy. That's why the inside of bends, especially where you see coarser, darker gravel, are classic places to check. Another key feature is bedrock. Whenever the bottom of the creek is solid rock instead of loose sand or mud, any crack, hole, or step in that rock can act like a trap. During floods or heavy rain, the water gains a lot of energy and carries everything it can: wood, mud, rocks, and minerals. As that energy drops, the heaviest pieces fall into those cracks and pockets and stay there. Over years and years, a small depression in bedrock can accumulate garnets, metallic minerals, and if the geology upstream is right, tiny diamonds. If you see exposed bedrock in a shallow creek, especially with visible cracks filled with dark gravel, that deserves your attention. Now let's talk about indicator minerals, because they're the language the creek uses to tell you what's going on upstream. One of the most important is garnet. In many diamond-related environments, you'll find small garnet grains in the creek gravel. To the naked eye, they usually look like tiny, dark glass beads, often red, wine-colored, or reddish-brown, sometimes almost purple. They're noticeably heavy for their size, and once cleaned, they show a bright glassy luster. Many of them look slightly rounded because they've been tumbled by water for a long time. Seeing garnets in a creek doesn't guarantee diamonds, but it tells you that the system is carrying material from deeper or more metamorphosed rocks, which is exactly the kind of environment where diamonds can form. Alongside garnets, pay attention to the dark, heavy sand that often stays in the bottom of your pan or sieve when everything else is washed away. That black sand is typically a mix of different heavy minerals. Among those, two are especially interesting for diamond hunters: ilmenite and chromite. Ilmenite is usually black or very dark gray, with a subtle metallic sheen, almost like dull steel. It's quite heavy and may show small, shiny faces when you turn it under the light. Chromite is also black, but tends to be even denser and has a more rough, lumpy appearance, sometimes looking like tiny pieces of lead. Both ilmenite and chromite are associated with deep, ultramafic rocks and some volcanic systems related to diamonds. Finding them together with garnets and creek gravel is a very good sign that you're dealing with material coming from the right type of rocks upstream. In some areas, you may also find unusual rock fragments that don't match the more common local stones. They might be greenish or dark gray rocks with small black spots, or crumbly, altered pieces that look different from regular river cobbles. These can be fragments of ultramafic rocks or even strongly weathered kimberlite or lamproite. You don't need to memorize all these names, but you should train your eyes to notice when the creek's gravel suddenly changes character. If you move from an area full of light-colored quartz and sandstone pebbles into a stretch with dark, heavy gravel, garnets, and black metallic grains, that's telling you something. Once you've identified a promising stretch of creek with indicator minerals, it's time to stop only looking and start processing material. The goal now is to let the differences in size and weight work in your favor, concentrating the heavy minerals into a much smaller volume so your eyes and your hands can actually keep up. That's where sieves come in. You don't need expensive or professional equipment to get started. A small set of sieves with different mesh sizes is more than enough. Think of it as a simple filter system. The coarsest sieve keeps out big rocks and debris, the middle one catches medium-sized pieces, and the finest one holds the small grains where most garnets, black sand, and tiny diamonds tend to hide. If all you have is a couple of stacked kitchen-style sieves with different mesh sizes, that already works as long as they're sturdy enough to handle gravel. The first step is to pick a specific working area instead of randomly scooping everywhere. Focus on inside bends where you see a bar of gravel, on the downstream side of big boulders and logs, and on spots where the creek narrows and the current was strong enough in past floods to drop heavy material. If there's exposed bedrock with pockets and cracks, that's even better. Scoop gravel from right on top of those features and from any dark, compacted layer just above the bedrock. With your coarse sieve in hand, load it with a reasonable amount of gravel, not so much that you can't move it. If the water is shallow and calm enough, you can submerge the sieve a little and start making gentle circular and side-to-side motions. The water will help wash away clay and silt. Lighter stones will move more easily, while the heavier ones settle toward the bottom. If you're stacking sieves, keep the finer one under the coarse one, so anything that falls through is caught instead of being lost back into the creek. After a short time, you'll see that the coarse sieve is left with only larger rocks. Take a quick look and remove anything obviously too big or too light. Some larger stones might still be interesting if they look unusually heavy or have metallic or glassy surfaces. But in general, your best material will be caught in the smaller meshes below. Move down to the next sieve, repeat the same washing and swirling motion, and then to the finest one. On the finest sieve, something important starts to happen. When you swirl and tilt it in a shallow pool of water, the lighter grains spread out, and the heaviest ones begin to form a band or a small concentration in one corner or along one side. That concentration is where the garnets, ilmenite, chromite, and any very dense clear grains will tend to sit. Spread that band out gently with your fingers or a small tool and examine it under good light. You're looking for tiny round red grains, garnet, very heavy black grains with metallic luster, and small transparent or slightly colored grains with a stronger shine than normal quartz. You won't find a diamond in every load of gravel, and you shouldn't expect that. At the beginning, consider it a win. just to see garnets and black sand piling up consistently. That means you're in the right environment and using the technique correctly. As you gain practice, your eyes will become much quicker at spotting anything that looks different. When you do find a small, clear, or pale stone that seems heavier than it should be, or has a strange metallic or oily luster, pick it out, rinse it carefully, and store it in a small vial or labeled bag. Don't worry about confirming it on the spot. All you need in the field is to separate interesting from clearly common. If your local creeks dry up during part of the year, that actually gives you an advantage. You can dig gravel from promising spots in the dry bed, bring it home in buckets, and run it through your sieves in a tub of water in your backyard or garage. The physics is exactly the same. You're using water, motion, and gravity to separate heavy minerals from the rest. Working at home also allows you to take breaks, use better lighting, and spend more time examining the concentrates without rushing. The important thing is consistency. The more buckets you process from the right type of gravel, the better your chances of eventually pulling out that first tiny diamond. Now let's jump to the moment everyone dreams about. You've done your homework, chosen a good creek, found garnets and heavy black sand, worked carefully with your sieves, and after several attempts, separated a few small stones that look different from the rest. Maybe they're colorless or slightly yellow. Maybe they look a bit greasy on the surface, and they feel heavier than their size suggests. How do you know if you've really found a diamond or just another piece of quartz or glass? The first thing to pay attention to is luster, the way the surface reflects light. A rough diamond doesn't sparkle like a cut stone in a ring, but it still has a very intense, sharp shine called adamantine luster. To the naked eye, that often looks like a mix of metal and very bright glass. Sometimes, especially in creek-worn stones, the surface can look slightly oily or waxy at the same time. Common quartz, on the other hand, has a more ordinary glassy luster, similar to a piece of broken bottle or window glass. If you place a suspected diamond next to a quartz pebble and move them both under a light, the diamond's reflections usually look crisper and more concentrated. Shape is also a clue, though not a rule. Diamonds that come straight out of hard rock deposits can preserve more of their original crystal form with recognizable faces and edges. Diamonds that have spent a long time in rivers and creeks tend to be more rounded, almost like tiny polished pebbles. They might still show traces of crystal faces, but smoothed by wear. So don't expect a perfect geometric crystal in a creek. Expect something small, dense, and slightly rounded with an unusual shine. Next comes hardness. Diamond is the hardest natural mineral, sitting at 10 on the Mohs scale. That means it can scratch any other common mineral, but virtually nothing will scratch it. You can take advantage of this with simple tools, as long as you're careful. One classic test is to gently try to scratch a piece of ordinary glass, like from an old jar or a picture frame. Clean both surfaces, press one edge of your suspect stone against the glass, and drag it firmly in a straight line. If nothing happens, the stone is probably too soft. If it leaves a clear, sharp scratch, that means the stone is at least as hard as quartz or harder. Quartz can also scratch glass, so this doesn't prove it's a diamond, but it does tell you that you're not dealing with something soft. To go a bit further, you can test whether the stone itself is easily scratched. A steel file or a very coarse sandpaper can be used very carefully on a tiny corner of the stone. If that corner gets visibly abraded or frosted with light pressure, the stone likely isn't diamond. Diamond resists scratching so well that, in practice, no common household tool should mark it easily. Be gentle and always test on a small area you don't mind damaging in case it turns out not to be valuable. Density is another powerful check. Diamonds are heavier than many common minerals of the same size. Quartz has a density of about 2.6, while diamond sits around 3.5. You can feel the difference with experience just by tossing similar-sized stones lightly in your hand. But there is a simple home experiment you can do if you have a digital kitchen or jewelry scale. First, weigh the stone in air and write down the weight. Then, fill a glass with water, tie the stone to a thin thread, or place it in a small, very light container, and submerge it completely in the water without letting it touch the bottom. Weigh it again while it's underwater. The difference between the two readings gives you an idea of how much water was displaced, which is related to the stone's volume. If you divide the weight in air by that difference, you get an approximate density. If the result is close to 2.6 comma, it's more likely to be quartz. If it's closer to 3.4 or 3.5 comma, it's behaving more like a diamond. At that point, the smartest move is to take it to a professional gemologist or an experienced jeweler who can confirm the identity with more advanced tools, even if it turns out not to be a diamond. By now, you already understand how diamonds can end up in creeks, how to read the behavior of water and gravel, which indicator minerals to look for, how to use sieves to concentrate heavy material, and how to run basic hardness and density tests. So it's time to talk about the big question that everyone has sooner or later. If you really find a rough diamond in a creek, how much can that stone actually be worth? The first thing you need to know is that diamond pricing is complex. The value of a diamond, even in rough form, depends on several factors at the same time: weight in carats, color, clarity, shape, and how much of the rough stone can be turned into polished gems. There's no universal fixed price per carat for a rough diamond. Instead, there are ranges, and those ranges change over time as the market moves. On the low end, you have rough diamonds that are only good for industrial use. These are stones that are too included, too fractured, too cloudy, or too dark to be worth cutting into jewelry. Industry uses them for cutting, drilling, and grinding tools. Many of these lower-grade stones are sold in parcels, where the price per carat can be relatively low, especially compared to high-end gem material. As quality improves, so does the price. Commercial rough diamonds with reasonable color and clarity that can produce decent polished stones can sell for much more. In this range, a stone's value might move from tens of dollars per carat into the hundreds of dollars per carat, depending on size and overall appearance. When you look at individual rough diamonds sold for gem purposes, especially in the 1 to 3 carat range, the numbers can rise quickly. A clean, well-shaped rough diamond of 1 or 2 carats can sometimes reach several $100s per carat or more, again depending on how it is expected to cut and what the resulting polished stones will be worth. For particularly attractive rough, the price can go into the low thousands of dollars per carat. What does all that mean for a creek diamond? Realistically, most of the first diamonds that hobby prospectors find in creeks are small, often under 1 carat, and may have noticeable inclusions or color issues. Many of them would fall closer to the lower or mid part of the price spectrum, especially if sold to a dealer who has to cover cutting losses, certification, operating costs, and profit. It's completely possible for a tiny included stone to be worth something like tens of dollars, not thousands, even though it's still a real diamond. But there is also the other side. If you happen to find a rough diamond in the 1 to 3 carat range with good clarity, decent color, and a shape that cutters like, the potential value rises quickly. A stone like that might be placed in a category where hundreds of dollars per carat or more are realistic, and in some cases it can reach into the low thousands per carat, depending on how it will cut and what the polished gems are expected to be worth. That means a single good crystal could represent enough money to cover your equipment, several prospecting trips, and still leave a solid profit. Above that, for larger and cleaner stones, prices can become very impressive. High-end rough used to create luxury jewelry, especially in larger sizes with excellent color and clarity, can sell for several $1,000s per carat. Unique top-quality stones can go way beyond that when they reach auctions. But those are exceptions that almost never come from casual creek prospecting. Still, it's important to understand that the range exists so you don't dismiss a good stone just because it came out of shallow water. The key is to stay balanced. Don't go into a creek expecting to pull out a life-changing stone on your first day, but also don't underestimate what you find. A small, imperfect diamond may have modest monetary value, but huge practical value, because it proves that your creek is truly diamond-bearing. From that moment on, every bucket of gravel you process isn't just a guess, it's a calculated effort in a confirmed area. But before you rush out to start searching for rocks that could be worth a fortune, there's one last thing you need to remember. Even if the stone you find isn't a diamond, that doesn't mean it has no value. A lot of people pick up an unusual rock in a creek, assume it's just another pebble, and either throw it away or give it away for almost nothing, when it could actually be a garnet, a sapphire, a piece of jade, or another gemstone. That's exactly why I created the book Gemology Journey for Beginners, available on Amazon. It's a straightforward, practical guide for anyone who wants to learn how to identify the most common types of gems and minerals, even without professional tools. Inside, you'll learn simple hardness, density, texture, and luster tests using everyday objects, so you can understand what you really brought home instead of guessing. With this knowledge, you won't have to rely on luck or someone else's opinion. You'll be able to decide what to keep, what to sell, and what to add to your collection with much more confidence. Now, if you're still taking your first steps or just not ready to grab the book yet, that's perfectly fine. You can still subscribe for free right now and watch the next video appearing on your screen, where you can learn more about gem hunting secret techniques. Thanks for liking and subscribing. Good luck, gem hunter.